Hello, welcome back. This is the part 2 for DC biasing. Okay, so we have ended our first video about the DC biasing for BJT with fixed bias configuration, and we have concluded that fixed bias configuration is very simple in the construction because you will only be needing two resistors, RB and RC. But we found out that upon changing the value for beta, the circuit is not very stable. So what we're going to do is we're going to look for another type of circuit that will improve the stability that we didn't have in the fixed bias configuration. So what is that circuit? So that circuit is the emitter stabilized bias circuit. So upon looking at the circuit, what did you notice? So it is just like a fixed bias, but this time we have a resistor which is placed across your emitter. So we will be calling that resistor as our resistor RE. Okay, so what are we going to do for this type of configuration? Just like what we did in our fixed bias configuration, we will try to divide the circuit into two parts. Okay, so the input side and the output side. So we will be calling the input side as your base. We will be calling it as your base emitter loop. Okay, so how does your base emitter loop looks like? So it's just like what we did in the fixed bias configuration, but this time with the addition of our emitter resistance. So we have here your VCC, and then this is your RB, and then this is our base. We have here your emitter. So before it is grounded, but this time we have your RE here. Okay, and then we will be joining the negative VCC and the ground. This is still under common emitter configuration because as you can see, emitter is still the terminal which is grounded. So emitter is still the terminal that we can see both at the input side and at the output side. Okay, so what we have here is the current flowing across our RE is your emitter current. The current which flows across your RB is your base current, and at this point you have your plus and minus VBE. Okay, so applying KVL, what do we have? So by applying KVL, you have positive VCC minus, you have IB, RB, you have minus VBE minus IE, RE is equal to 0. Okay, so unlike in the fixed bias configuration, we cannot solve right away for IB. Why? Because in this case, we have two unknowns. You have IB and you have IE. But as you can remember, we have a relationship showing we have a formula showing the relationship between our IB and our IE. And what is that? We have a formula wherein we have IE is equivalent to beta multiplied by beta plus 1 multiplied by IB. So in this case, if we're going to substitute this with this equation, we are going to have an equation having only one unknown, which is your IB. So what will happen then? So if we're going to do that, it will become VCC minus IB RB. Okay, so you have minus VBE, so you have minus IE. But what is IE? IE is beta plus 1 multiplied by IB multiplied by RE is equal to 0. Okay, so in this case, we only have one unknown. So what is our unknown? That is your IB that we can solve for IB. So what is IB now? IB is equal to VCC minus VBE all over. So you have there, factoring out your RB, your IB. So you have RB plus, you have beta plus 1 multiplied by RB. So this will be our formula now for IB. Okay, so what's the difference? We have an additional resistance in our denominator plus the appearance of your beta. So IB now is a factor, beta now is a factor of your IB. Whenever beta changes, that likewise IB will change. Unlike in the fixed bias configuration, when beta changes, IB remains the same. So it has a very big impact on IC. So why? Because just like in the fixed bias configuration, upon solving for IB, we can now solve for your IC. So what is your IC? It's the same. IC is still equal to beta multiplied by your IB. Okay? So what we have here, what interesting part that we have here is at the input side, we didn't only see RE or the emitter resistance, but we have seen a different resistance, a higher resistance than the normal emitter resistance. Why? Because at the input side, we have multiplied your emitter resistance with beta plus 1. So beta plus 1 is a high value, therefore we are increasing the original value of our emitter resistance. So like this one, okay? So instead of just saying RE, what do we have? We have a very high value for RE. So we have this network as derived from the previous equation that we just derived a while ago. So in this case, what we actually saw is not just RE, but a very high input impedance or an input resistance. We call that Ri, and that is equivalent to the emitter resistance multiplied by beta plus 1. So we are looking, or we are seeing a higher resistance at the input side. Okay, let us see what will be the impact for this one. Before we go to that, we will go back. Okay, so we will go back to the output side. So what is the output side? So let us go back to the output side and let us see what will be the difference. So the output side is the output side is the base collector. So we have the base collector loop. So what do we have in the base collector loop? So in the base collector loop, we have your VCC here. And then we have your RC connected at the collector side. And then you have your RE here connected at the emitter side. And then the ground is connected to the negative terminal of your VCC. So this is your output side, or the base collector loop. We have here, the current flowing here is your IC. So the resistance here is your RC. And then we have here your collector to emitter junction. So we call this as your VCE. So you have plus or minus VCE here. So what is the current flowing here? This is IE because this is RE. But what is the relationship between IC and IE? So we said that IC is approximately equal to your IE. So therefore, whatever IC that we have solved in the base emitter loop will be the same IC that will flow across your emitter resistance. Okay, so by KVL again, we have here following this loop. So we have plus VCC. So Current entering, this is plus. Current leaving, this is minus. Current entering plus. Current leaving, this is minus. So we have your plus VCC. So you have minus IC and RC. So we have minus VCE. So we have minus IE, RE. But since IC is approximately equal to IE, so we will be using IC multiplied by RE. That is equal to 0. Okay? Factoring out your IC here. So we will be having VCC minus IC, RC plus RE minus VCE is equal to 0. Then we can solve for your VCE. Okay, so what is your VCE? VCE is equal to VCC minus IC RC plus RE. The only difference with the fixed bias configuration is, in the fixed bias configuration, this is only VCC minus IC/RC. So at this time, we have RC plus RE. So that is the only difference from the fixed bias configuration. Okay, and this time, class, VE is not anymore equal to 0. Why? Because we have already a resistor that is connected into your emitter region. So therefore, in this case, your VE is no longer equal to 0, unlike in the fixed bias configuration. Okay, so there will be slight changes in solving for the collector voltage and the base voltage, and this time we have an emitter voltage that we can solve. Okay. So let us try solving this problem just like what we did in our fixed bias configuration. We're going to try to change the value of the beta. So we will be starting to solve this problem first by using beta is equal to 50, and then just like what we did in the fixed bias configuration, we're going to solve this when beta is equal to 100. And let us see if we have an improved stability using this particular circuit. So I have already solved that value. So we have here, what will be the starting point? So the starting point is we're going to solve for IB. Okay, so what is IB? As shown here using the formula. So this is VCC minus VBE. Okay, so it's alright if you cannot, I suggest you do not memorize the formula. So what we did earlier, we just derived it from the equation. So it is simple. It is easier just to derive it than to have it memorized. Okay, so we have here IB, which is equal to VCC minus VBE divided by RB plus beta plus 1 RE. So looking at the circuit in the PowerPoint presentation, so we solve for the value of IB, which is equivalent to 40.1 microamperes. And then we solve for IC. IC is beta multiplied by IB. So multiplied by 50, we have an IC which is equivalent to 2.01 milliamperes. Okay, so if you want, you can press your calculator so that you can practice solving for this type of problem. And then we can solve for your VCE. So VCE is equivalent to VCC minus IC multiplied by RC plus RE. So those are just given, so it is just direct substitution from the equation, and then we can solve for the value of VCE, which is equivalent to 13.97. Now let us solve for VC. So before, if you can still remember, when solving for fixed bias configuration, we have your VC. For fixed bias configuration, we have your VC is equal to your VCE. So why? Because as you can see, VCE is equal to VC minus VE. And for fixed bias configuration, VE is shorted. It is equivalent to 0. That's why VC became equal to VCE. But that is not the case already. Why? Because we have a resistor placed in your emitter terminal. So therefore, VE is no longer equal to 0. So therefore, VC is not equal to VCE anymore. So the first thing that will come to your mind is that when we try to solve for VC, so what is your immediate formula for VC? Okay, so you might be thinking, since this is VC, this is equal to IC multiplied by RC. Okay, so that is our the first thing that will come to our mind. Why? Because of Ohm's law. So just like what we learned during your circuit analysis. But let us analyze first, what is VC? Where is VC, by the way? Okay, so VC is the voltage across the collector and the ground. Okay, collector going to the ground. And when we say VC is equal to ICRC, this is the one that you are computing for. So this is IC multiplied by RC. But where is VC? VC is from the collector going to the ground. So I will be asking you, is it the same? Is it the same? No, it's not. Therefore, VC is not equal to IC multiplied by RC. Okay? Rather, VC is equal to, so the voltage across the collector going to the ground. So you can see VC is the sum of your VCE and the voltage across your RE. Or, one more thing, VC is equal to the VCC minus the drop across here. So you have your VCC minus your drop across here. So the remaining voltage is your VC. Get that? So we have here VC. Okay? Your VC is equal to VCC minus ICRC, not VC is equal to ICRC. Okay, so VC here is 15.98 volts. What is VE now? Okay, so we said VE is equal to VC minus VCE. So VE is equal to 2.01. This time, can we make use of VE is equal to IERE? Okay, let us go back to your circuit. Where is VE? VE is the voltage from the emitter going to the ground. Emitter to the ground. So what is the voltage that you are seeing from the emitter going to the ground? So that is the voltage across your emitter. And what is the voltage across your emitter? The current flowing across your emitter multiplied by your emitter resistance. And that is your IE, which is approximately equal to IC multiplied by resistor RE. Okay? So, in this case, we can make use of your Ohm's law. So in this case, we can make use of your Ohm's law. And your VE here is equivalent to 2.01 volts. Or that is VC minus VCE. So this is 2.01 volts. Or 2.01. So that will give you the same answer. Okay? So a while ago, we say that your VC is just equal to your VCE plus your VE. So when you say VCE, that is 13.97 plus you have your VE 2.01, that will also give you the same value, which is 15.98 volts. Okay, but VC is not equal to IC times RC, so they are not equal. So either you're going to make use of this or you're going to make use of this. So that is your formula for VC. Okay, so one thing more, is your VB. Okay, so how do we solve for VB? Going back to your fixed bias configuration, we have your VB, okay, is equal to your VBE. Why? Because VBE is equal to VB minus VE. And that time, your VE is shorted, so therefore your VE is equal to 0. So this time, VE is no longer equal to 0. So therefore, VBE is not equal to VB. Okay, again, what is VB? So VB is the voltage across the base and the ground. So the first thing that will come to your mind is that, is it VB equal to IB times RB, just like your Ohm's law? Okay, so let us look at the circuit. So by looking back at the circuit, where is VB? VB is at the base going to the ground. So what can you see? Base to the ground. So it is the VBE and the voltage across your emitter. Where is IBRB? IBRB is the voltage across your 430 kilo ohms. And the voltage across 430 kilo ohms is not equal to VB because VB is from this terminal going to the ground. So what is VB then? What is VB then? So we can solve for VB using this formula. So VB is equal to your VBE plus your VE. So this is equivalent to 0.7. Since we have already solved for VE earlier, plus 2.01, VB is equal to 2.71 volts. Or we have an alternative solution. It is the VCC less your IB, or the drop across your resistance. Okay, so we can make use of this one. So VB is also equal to the VCC minus IB multiplied by RB. Let's do that. So what is our VCC in this case? So we have 20 minus our IB is 2.01 milliamperes and our RB is equivalent to 430 kilo ohms. So if we're going to solve for that, that will give you 20 minus 2.01, sorry, that's IC. IB is 40.1 microamperes. So minus, so this is 20 minus 40.1 micro times 430 kilo. 20 minus 40.1 exponent minus 6 times 430 kilo is equal to that. So this is approximately equal to 2.75. So almost the same. The only difference is because we have done some rounding off, but as you can see, it's around 2.7. So it's either you use this one or you use this one, but VB is not equal to IB times RB. Remember that. Okay? So lastly, like what we did in your fixed bias configuration, we computed for VBC. So what is VBC? VBC is VB minus VC. So using your using your answers from the previous one, so you have 2.71 minus 15.98. So that will give you negative 13.27. Again, we have a negative answer. So what's the meaning for the negative answer? Because we have here a reverse bias. So that's it. Okay? So this is using beta, which is equivalent to 50. So what we did in fixed bias configuration is we tried to increase the value of our beta. So from 50, we make it equal to 100. Okay, so we will be doing that also. So using the same formulas, we have here your beta is now equal to 100. So this is your new value for IB. This time IB changed because it is already dependent on the value of beta. So when beta changes, IB is already, also changed because of the appearance of your beta parameter in the formula for the base current. So we have here 36.35 microamperes, and then solving for IC, we have here 3.63 milliamperes, and then solving for VCE, we have 9.11 volts. Okay, let's compare. There is still a change. Okay, so we didn't say that it will not change, but look at the change that occurred. Okay, when comparing the two, when we have beta equal to 50 and equal to 100, so we have a change, but not as abrupt change as with the fixed bias configuration. In the fixed bias configuration, you remembered what happened to IC when the beta doubles, so as the value for your IC. So this time there is a change, but not as big as the change that happened in the fixed bias configuration, and also with the VCE. So comparing the two, so these are our previous results from the previous video. So as you can see, there is a change in both of them, but this has a much lower impact compared to the fixed bias configuration. That's why we can say that emitter stabilized configuration is more stable compared with the fixed bias. Also, although we will not stop here yet. Why? Because there's still a change. So it is not very stable yet. But still, there is already an improvement. So where is the improvement then? So the improvement is when we place the emitter resistance. So that's why it is called the emitter stabilized configuration, because the stability, the additional stability was due to the presence of your emitter resistance in the circuit. Okay, so that's your second circuit. A little more complicated compared with the computations that we did in the fixed bias configuration, but what we have is a better stability. Okay, so that's our second circuit. So we will not stop there. Why? Because as you can see, it is not yet very stable. So we will be going to our third configuration. And what is our third configuration? Our third configuration is, sorry, we will not go with our third configuration, but we will go to our saturation level. So for fixed bias configuration, the saturation level, our IC sat, is equivalent to VCC all over RC plus, or all over RC only. So this time, how do you compute for the IC sat? We usually place a short circuit between your collector and your emitter terminal. So upon placing a short circuit here, IC saturation will be flowing across your circuit. And what is that? That is VCC divided by the collector resistance plus the emitter resistance. So the difference between fixed bias IC sat is VCC all over RC. For emitter stabilized, IC sat is VCC all over RC plus RE. So just the additional RE. So what do we expect? We expect a lower saturation voltage or a lower saturation current for emitter stabilized compared with fixed bias configuration. Okay. Another thing is the load line analysis. So since in the load line analysis, we have our output value, which is equal to VCE is equal to VCC minus IC RC plus RE. So we can establish your 2 points by using this specific formula. Okay, so when we set IC be equal to 0, so what do we have? We have your, when IC is equal to 0, you have your VCE is equal to your VCC. So this is a point at the X axis or at the horizontal axis. So where is that? That is your first point. And then your second point is when we say VCE is equal to 0. So when your VCE is equal to 0, we can solve for your IC, which is equivalent to VCC all over RC plus RE. So where is this point? This point is lying at your y-axis. So where is that? This one. So the difference with the fixed bias configuration is this is only divided by RC. So this time it is dependent on both values of RC and your R. So this is the load line analysis for emitter stabilized configuration. Okay. Next. So the third and the most widely used transistor amplifier circuit is the voltage divider bias. So in the voltage divider bias, you can see we have, instead of RB here, we have R1 and you have your R2. So for fixed bias, we only have RB and RC. For emitter stabilized, we have your RE. And for voltage divider, we have an additional resistance, which is your R2. So we are trying to establish a point here that your Q point must be fixed or it will not change abruptly. Okay, so we are trying to look for a circuit. We're trying to establish a circuit wherein your Q point here, which is directly dependent on your ICQ and VCEQ. So we're trying to find a circuit wherein your ICQ and your VCEQ will not change at all, even though the value of beta changes. Okay, so it is not like the fixed bias nor the emitter stabilized configuration. So why is it called voltage divider? So in voltage divider configuration class, we have two approaches here. So we have the exact solution and we have the approximate solution. So we can use the exact solution using any voltage divider circuits, but approximate configuration or approximate approach is only used when we have satisfied a specific condition. So what specific condition is that? We will be finding that out later. Okay? So for the exact analysis, we are going to redraw the input side and we're going to Theveninize that specific circuit. So do you still remember how do you Theveninize your circuit? So you have to convert that specific circuit to a single resistance with a single voltage source. So the single resistance will be connected in series with the single voltage source. So we will be calling the single voltage source as your ETH or your VTH, while the equivalent resistance will be called the RTH. So this is just a review from your circuit analysis lecture. So this is the redrawn input side for DC analysis. So your VCC is connected to your R1. Your R1 is connected to your R2. So the intersection of your R1 and R2 is connected to your base. And then your R2, likewise your VCC, is connected with your RE. So we are going to Theveninize this specific circuit, the circuit in the blue box. So how do you Theveninize that? We are going to convert this into a single voltage source in series with a single resistance. So the first thing that you're going to do is you're going to solve for the RTH. So what is your RTH? RTH is your Thevenin's resistance. So this is the Thevenin's resistance that can be measured or can be solved when you replace all your sources by a short circuit. So since we only have one voltage source, we're going to replace that voltage source with a short circuit. So this is your VCC. So when this is shorted, and we're going to look for your RTH in this manner, looking through your RTH, we're going to find out that the relationship or the connection of R1 and R2, they are in parallel. So what is RTH? RTH is R1 which is in parallel with R2. Okay? So, how do we solve for your Thevenin's voltage? We are going to bring back your voltage source. So, for Thevenin voltage, which is ETH, VCC is now returned to the network and the open circuit Thevenin voltage is determined. So, where are we going to determine? So, where did we cut the circuit? We cut the circuit across your R2. So, whatever the voltage across R2, that will be your Thevenin resistance, okay, or your ETH. So using voltage divider configuration, because R1 and R2 will just divide your VCC, the voltage across R2 is equivalent to VR2, which is also equal to R2 multiplied by your VCC divided by R1 plus R2. And then we're going to replace the original circuit with the Thevenin's equivalent circuit. That is, we're going to connect your ETH and in RTH in series, and then we're going to bring that back into your original circuit. So this is now your Thevenin's equivalent circuit. Okay, so your RTH is connected at your base and then with your RE. So upon knowing your RTH and your ETH, the first thing to do is to solve again for IB. So we will start solving again for IB. So what is IB? So the base emitter loop again. So for the base emitter loop again, we will be having there, instead of VCC, we have already there your ETH. So I have ETH minus, instead of RB, we have IB multiplied by RTH. And then you have minus VBE, and then you have minus IE multiplied by RE is equal to 0. However, what is IE? IE is equal to beta plus 1 multiplied by IB. So substituting that in the formula, you have ETH minus IB multiplied by RTH minus VBE minus beta plus 1 IB times RE is equal to 0. Okay, so we only have one unknown, wherein our unknown is your IB. So what is your IB here? How do we solve for IB? So factoring out IB, we have here ETH minus VBE all over RTH plus beta plus 1 multiplied by RE. So this is your formula for IB. So this looks exactly like your formula in the emitter stabilized configuration. But in the emitter stabilized configuration, instead of ETH, you have VCC. And instead of RTH, you have RB. But the format it is the same. Okay? So, what's next? What's next is, we will solve for IC. IC is still equal to IB beta multiplied by your IB. So we can still see beta there, okay? But later on, we're going to find out what will be the effect of this particular circuit, okay? Then, looking at the base collector loop. So the base collector loop for voltage divider, which looks like the emitter stabilized. configuration. So what do we mean by that? Everything is the same at the output side. So the only difference is at the input side. So we can say that VCE is still equal to VCC minus IC multiplied by RC plus RE. So the IC SAT and the load line analysis, since both of them happens at the output terminal and at the output terminal, nothing changed with our circuit, so that means it is the same. Okay, so no problem with the output side, just at the input side. Okay, so let us try solving some problems. We are asked to solve for VCE and IC. Okay, so just like what we did in fixed bias configuration and emitter stabilized configuration, we will see dati saan ba ito nakasaksak? We're going to okay, so we're going to compare the value of IC and VCE when your beta changes, okay, using the voltage divider configuration. So this is the circuit. I have already here the sampled problem. So first, using beta, which is equal to 140, and then using the exact analysis first. So using the exact analysis, what do? We solve for RTH. So RTH is R1 parallel R2. So we are given 3.55 kilo ohms. And then we solve for the VTH or the ETH, that is the voltage across your R2. So by voltage divider, so we have solved for the value of ETH, which is 2 volts. And then by using the formula, we have your IB, which is equivalent to 6.05 microamperes. So knowing IB, using beta equal to 140, so we have here 846.31 microamperes, okay, or around 0.85 milliamperes. Solving for VCC, we have 12.27 volts. Okay, now, what happens now if beta is equal to 280? So we double the value of your 140. So in this case, your RTH and your ETH will remain the same because RTH and ETH um, is not dependent upon the value of beta, so it will be the same. So what happens is your IB will change when the value of your beta changes. So in this case, our beta is 3.06 microamperes. So knowing your IB, we can solve for IC. Look at your IC now. Your new IC is equal to 856.33 microamperes, or this is about 0.86 milliamperes. Look at the difference, class. We have 0.85 milli and 0.86 milli. So it looks like it doesn't even the change is very very small. So the difference is very very small. So we can say that this is a more stable circuit. So this is what we mean by, even though your beta doubles, still we can see that your Q point, which is dependent on your IC and your VCE, is almost not changing. Okay, so this is our explanation when we say that the circuit is really stable, unlike the previous two that we have just discussed. And then what happens to your VCE? VCE is 12.15 volts. So upon comparing the two, look at this. Although your IB changed, but IB is very, very small. So Q point is really dependent on your IC and your VC. So they are the two important parameters. So as you can see, your IC is 0.85 and 0.86 milliamps. This is 12.27 and this is 12.15 volts. So we can say that this is quite an interesting point. So we can say that among the different types of circuits that we have, voltage divider is really the considered as the most stable. That's why it is usually the one which is always being used. Okay? But the downside here is that the the procedure or the process is very long because we need to get first your Thevenin's equivalent circuit. Now, we have an additional, or we have a what do you call this, another approach in solving for this. Okay, so we have a another solution in solving for this, and we will be calling that, so we will be calling that class the approximate analysis. So the first is the exact analysis. So you can use exact analysis using any circuit, any voltage divider configuration. All of them can be solved using the exact analysis. The approximate analysis is a shorter one. Okay, so the procedure here or the process here is shorter, but it is not used for all. So we have to satisfy a certain condition so that we can make use of the approximate analysis. So how are we going to use the approximate analysis? Okay, so Ri, so we have already mentioned Ri in our emitter stabilized configuration. So your Ri is what you can see at the input terminal. It is not really equal to your Re, but rather it is being increased by a factor equivalent to beta plus 1. So Ri is the equivalent resistance between base and the ground for a transistor with an emitter resistor. So Ri is applicable to those circuit with an emitter resistor. That's why we didn't mention Ri in your fixed bias configuration. So just like your emitter stabilized, voltage divider also has an emitter resistor. Okay, so Ri is being reflected at the input side by the value of beta plus 1 multiplied by the actual value of your Re, making the value of your Re bigger than the normal emitter resistance value. Okay, so when you say that Ri is very, very high, so how high is your Ri? It is greater than R2. So this is your R2. So when your current flows across your VCC at this point, class, your current will be dividing into two. So your I1, which flows across your R1, and your I2, which is flowing across your R2. So I1 is equal to IB multiplied by I2. So because this is flowing across your base terminal. Okay? So, however, when your R1, Ri is very, very large, so when your Ri is very, very large, your current doesn't want to pass through this larger value. So where does the current want to pass? The current always chooses the least resistance path. And when this R1 here is very, very large, your almost all of your I1 wants to pass through your I2. So therefore, I2 is much, much greater than your IB. When that happens, I2 becomes approximately equal to your I1. And when your I1 is approximately equal to your I2, this R1 and R2 here became a series circuit. So that's why it is called voltage divider, because when R1 and R2 is already in series, your VCC will just be dividing between R1 and R2. That's why it's called voltage divider configuration. But this is not always the case. So for this to become equal, approximately equal, your Ri here, or the equivalent resistance between the base and the ground, should be much, much greater than R2. So, what will be our condition to satisfy? Okay, so we have to satisfy a certain condition. And that is, so when IB is approximately equal to 0, I1 is equal to I2, and R1 is in series with R2. So it is safe to use the term voltage divider because they are already in series. But it will only happen if and only if we satisfy this condition, and that is your beta RE must be greater than or equal to 10 times your R2. So, every time you will be doing the approximate analysis, you have to consider this one. So, if this is not satisfied, you can always use the exact analysis. But how easy is your approximate analysis? So, your approximate analysis, when we satisfy that condition, what we can have here is we can solve for the voltage. Okay, so we can solve for the voltage across, R2. So what is the voltage across R2? So since it is in parallel with the base and the ground, we can call that your VB, or the base voltage. Okay, so you can see the voltage across R2 is just the same as your voltage VB. And what is voltage across R2? So since they're already in series, we will be using the voltage divider. We will be using voltage divider principle. So VB will be equal to what? So VB is equal to VCC multiplied by R2 all over R1 plus R2. So once we know VB, we can solve for VE. So we have here VBE is equal to VB plus, VB minus VE, or VE is equal to VB minus VBE. Okay? So when you determine VE, you can solve for IE. What is IE? IE is VE divided by RE. Okay? And then what happens? When you know IE, we can use this instead. IC is approximately equal to IE. So did you see your beta here? No beta anymore. So even though we change the value of your beta, it will no longer be affected by the circuit. So therefore, we have found a circuit that is totally independent of our beta parameter. And beta parameter is very, very much dependent on temperature, okay, or any other circuit parameters. So we totally get rid of your beta. So when we solve for IC, which is approximately IE, so VCE will follow. VCE now is equal to VCC minus IC RC plus RE, just like the usual formula. So for approximate analysis, all you have to do is to solve for VB, and then we can solve for VE, and then we can solve for IE. IC is approximately equal to IE, and then we can solve for your VCE. Again, this is very simple, totally independent of beta, but you need to satisfy a certain condition. And what is that condition? Your beta RE must be greater than or equal to 10 times your R2. So if this is satisfied, therefore, we can make use of your approximate solution. Okay? So we have here, let us repeat the previous example, this time using the approximate analysis. Okay? So I have here prepared The condition for approximate analysis. So let us first check the condition. We have beta RE. Is it greater than or equal to 10 times R2? So that is 140 times 1.5 kilo ohms. Is it greater than or equal to 10 times 3.9 kilo ohms? So you have here 210 kilo ohms. Is it greater than or equal to 39 kilo ohms? Yes, we satisfy the condition. So since we satisfy the condition, we can make use of the approximate analysis. So in this case, we solve for VB first. So VB is the voltage across R2. So that is R2 times VCC all over R1 plus R2. So that is given by 2 volts. And then we solve for VE. That is VB minus VBE. So that is 2 volts minus 0.7. So that is equal to 1.3 volts. Then we solve for IE. IE is equal to VE all over RE. So that is equivalent to 866.67 microamperes or approximately equal to so 0.87 milliamperes, approximately equal to 0.85 milliamperes using the exact solution. So if we satisfy the condition, we can get an answer which is approximately equal. Okay, and then we will assume that IC is approximately equal to IE in solving for VCE. So VCE is 12.03 volts versus the 12.27 volts that we got using the exact formula. So as you can see, answers are approximately equal. Okay, and then we got rid of your beta. So what if we wanted to make your beta equal to 280? So did we see any beta in our formula? None. Okay, that means even though we change your beta to 280, it is automatically independent of your variable beta. So therefore, we have here a very, very stable circuit. And that is your voltage divider configuration. Okay, now, what if, okay, what if we are going to make use of this? Okay, what if What if we have a new circuit here and then we're asked to solve for IC and VCE using the exact and the approximate solution? Okay, so let us see the difference. So we have here the exact solution. So for the exact solution, you need to solve for RTH first and your ETH. And then you solve for IB. Upon solving for IB, we solve for IC, which is 1.98 milliamperes. And solving for VCE, you have 4.54 volts. Okay, so for the approximate solution, we are going to test if we satisfy the condition. So beta RE, is it greater than or equal to 10 times your R2? So upon looking at your condition, we can see that we didn't satisfy our condition. So what happens if we still use approximate solution even though the condition was not satisfied? Okay, so let us do that. So we have here, we solve for VB, it is the same 3.81, and then we solve for VE, and then you solve for IE, which is approximately equal to your IC. Look at the value. We have 2.59 milliamperes here compared to 1.98 milliamperes here. So as you can see, they are not approximately equal. So if we didn't satisfy the condition, therefore, let us not use the approximate solution just because the solution is easier. Okay, so what are we going to do? We will follow the exact solution. So we can just use the approximate solution once you satisfy this given equation here. Okay, so for the VCE, it is 3.88 volts.
It is equivalent to 3.88 volts compared to 4.54. So 3.88 is not approximately equal to 4.54. Therefore, why didn't we have an approximate answer? So a closer answer with each other. Why? Because we didn't satisfy this condition here. Okay, so we can only make use of the approximate solution when this condition is satisfied. Okay, so that is your voltage divider configuration. So voltage divider configuration is still a common emitter configuration. Why? As you can see, the emitter terminal is still the one which is grounded. Okay, so the emitter terminal is the one which is shown both at the input side and at the output side. Okay, so are we going to stop here? Because it is already the most stable configuration. So we have another one, although um, voltage divider is said to be the most stable circuit, but we still have another one, which is the DC bias with voltage feedback. Okay, so the improved stability using the DC bias with voltage feedback is obtained by introducing a feedback path from the collector to base. So what do we mean by a feedback path? When you say feedback, it is somewhat a connection connecting your output terminal to the input terminal. So what is the output terminal for common emitter? So this is still common emitter. Look at the configuration, look at the circuit. The emitter is still the one which is being grounded. Okay, so the output terminal is the collector, the input terminal is the base. We placed a feedback connecting your collector going to the base. So your RB here is connected to the terminal going back to the base. So we have a DC bias with voltage feedback configuration. Okay, so as you can see, if you're going to compute for the VCC, okay, so if you're going to compute for the base emitter, still have paper here, here. Okay, so going back to the base emitter loop, we are going to pass through your RC. Okay, so you have here your VCC, then you will be passing through your RC, and then you have a feedback here, that is your RB. Okay, and then your RB is connected, of course. So this is your collector, this is your RE, and then your RE is connected to your VCC. So this is your base emitter loop. Okay, however, if you're going to look at this, we call this IC prime, because this is your IC going to the collector and this is your IB. So what is your IC prime, class? Your IC prime is IC plus IB. Okay, but since IC is much greater than your IB, we can say that your IC prime is approximately equal to your IC. Okay, so what is the current flowing across your RE? That is your IE. So what is IE? IE is likewise IC is likewise approximately equal to your IC. Okay, so if we have a loop there, KVL, so what do we have? You have plus VCC, so you have minus IC prime RC. So I have plus minus, so I have plus minus, so I have minus IB multiplied by RB. So you have plus minus, this is VBE minus VBE. So you have plus minus, you have here IE multiplied by RE is equal to 0. So in this case, we have your IC, we have your IB, and we have your IE. All of your currents are in the single formula that we have. But this is where your approximations comes into place. So what is IC? IC is approximately equal to IC prime is approximately equal to IC, and IC is approximately equal to beta IB. Okay, so we have here VCC minus beta IB times RC minus IB RB minus VBE. What is IE? IE is approximately equal to IC. And what is IC? IC is beta IB. So we have here beta IB multiplied by RE is equal to 0. So what do we have here? What is our unknown here? The only thing that is unknown here is your IB. Okay, so factoring out your IB, we can solve for IB just like in the previous circuits that we have studied. So IB is equal to VCC minus VBE all over. You have RB plus beta RC plus RE. So this is your IB. Actually, we have a pattern here. Have you seen the pattern? Okay. I will be explaining the pattern later. So after solving for IB, what's next? We can solve for IC. So what is IC? IC is beta multiplied by IB. And then you can solve for VCE. So what is VCE? VCE is VCC minus IC RC plus RE. So by looking at the output side, the collector to emitter loop, the collector to emitter loop is just the same as with the emitter stabilized. It is the same with the voltage divider. So for DC bias with voltage feedback, it is just the same with our analysis using the emitter stabilized and using the voltage divider configuration. So therefore, your IC SAT, your IC SAT is the same. So IC SAT is VCC all over RC plus RE. Likewise, your load line analysis is the same. So what is your load line analysis? Your VCE is equal to VCC minus IC RC plus RE. So it is the same. So from the emitter stabilized to the voltage divider up to the DC bias voltage feedback, the collector emitter loop shares the same procedure. So the process are the same. So the only differs on the input side. Okay, so what is the procedure? You solve for the base current. After solving for the base current, you can compute for the collector current. And after solving for the collector current, you can compute for the voltage across the collector and the emitter. Okay, so let us see if this will have a good stability. Okay, so first, okay, so using this formula or using this problem, let us start with having a beta which is equal to 90. So solving for IB using the formula that we just had derived. And then we have here your IC, substituting that to our formula. And then we have your VCE which is equal to 3.69 volts. So kindly practice. Okay, so kindly try this at home. Since you don't have any other things to do, so kindly practice it. At the end of each chapters, there are exercises there. There are problems there. So kindly do some practice, problem analysis or circuit analysis so that you can understand it better. So if you are doing the computations more often, this will be very easy for you. Okay? So, and then finally, we solve for VCE, which is 3.69. So just like what we did in our early discussions, we try to increase or we try to double your beta. So from 90, we try to make this 180. So when that is equivalent to 180, just following the solutions that we had, and comparing them, so we have here 1.07 and 1.28. So not as stable as the voltage divider, but definitely it is better compared to the fixed bias and the emitter stabilized configuration. Okay, so if we're going to rank them, so the best or the most stable is the voltage divider configuration, followed by this DC feedback bias. Okay, but so we have four different circuits. So you might be wondering, we have too many formulas to remember, but no, don't memorize the formula. The important thing here is that that circuit is just the same. Even though you use any other books, when you search for fixed bias configuration, when you search for emitter stabilized, when you search for voltage divider and DC feedback, you will get the same circuit result. So therefore, do not memorize, because if you memorize, there are lots of formulas. So you don't memorize it. You just learn how to derive the different equations coming from those. And it is very simple, right? Let us summarize the four. So let us summarize the four. So for fixed bias, what is your IB? You start by solving for IB. Actually, everything you start from solving for IB. So IB is just your VCC minus your VBE all over RB. Okay, so knowing IB, you can solve for IC, so that is beta IB, and then you can solve for your VCE, which is equal to VCC minus IC times RC. So for emitter stabilized configuration, we have an additional RE. So you have your VCC minus VBE all over your RB plus your RE. But it is the input resistance which is being amplified or being increased by a factor equivalent to beta plus 1. So it will be beta plus 1 multiplied by your RE. But upon solving for IB, you can solve for IC, which is beta IB, and then you can solve for VCE, which is equal to VCC minus IC, since we already have RE, that is RC plus RE. For voltage divider configuration, we have your IB, so we have ETH minus VBE all over RTH plus beta plus 1 multiplied by RE. Just the same, okay? Just the same aside from your ETH and your RTH. But the format, okay? The format is the same. Current voltage divided by resistance. Okay? So what is IC? Beta IB. What is VCE? VCC minus RC, RC plus RE. And finally, for the DC feedback, you start with IB. So we have VCC minus VBE all over. You have RB plus beta, RE plus RC. So it's the same. Okay, by looking at the formulas, they are technically the same. IC is beta IB, and then VCE is equivalent to VCC minus IC RC plus RE. Okay, so those are the different common emitter configurations. All of them are common emitter. Why? Because all of them has the emitter terminal, which is the one which is being grounded. Okay, so the DC analysis part is not yet finished. So we will still have part 3 for this topic. Okay, so before I upload the part 3, so please stay at home, okay, keep safe, and while doing that, try solving some of the problems at the end of each chapter of your well-studied book. Okay, so please practice. If you have any questions, you can always send your message, and then you can still read your you read your textbook. I have given you your textbook in the school book. So please, okay, so please study, so that when we when classes resume, you already have an idea about this one, and then expect series of quizzes and exams when classes resume. Okay? Okay, good. Have a nice day. Bye.